So, ChatGPT is based on GPT-4, an advanced natural language processing model developed by OpenAI. GPT-4 is one of the largest and most powerful language models that is capable of understanding and at the same time generating human-like text across a wide range of tasks. So, let's check together the building blocks of ChatGPT, the key components: input representation, self-attention, positional encoding, and output generation. These are the four key components that make up the ChatGPT architecture. Each of these components plays a crucial role in enabling the model to process and generate human-like text based on user inputs. So before the model can process texts, it must be converted into a format that the model can understand. This is input representation. This input representation involves three tasks. The first one is tokenization. The second is vocabulary, and the third is embeddings. Tokenization breaks the text into smaller units. These units are called tokens. The vocabulary, the second step, contains the set of all the unique tokens the model is trained on. And finally, embeddings convert these tokens into continuous vectors that the model can process with various metrics inside. But let's dive into and see it in detail. Tokenization, breaking text into smaller units called tokens. These tokens can be words, subwords, characters, depending on the model's design. Tokenization allows the model to process text efficiently. But not only this, with tokenization, we can also identify patterns within the input. Let's see an example. Let's suppose that we have this phrase: ChatGPT is an AI language model. So we have the first level, the word level, tokenization word level. And you can see that here, each word is a different token. We have ChatGPT. This could be a JSON file. So the first word is ChatGPT. The first token is ChatGPT. The second one is. The third one is N. The fourth one AI. The fifth language. The sixth model. The seventh is full stop. Punctuation also matters here. The second level, the subword level, so in the word level tokenization example, the sentence is split into individual words and punctuation. In the subword level example, the sentence is split into smaller units, which can help the model handle rare or unknown words. So the choice of tokenization method depends on the specific natural language processing task and the model that is finally used. As you can see here, chat is one subword, G another subword, PT another subword, is an AI language model, the rest is as is. Nothing changes. The vocabulary is the set of unique tokens that the model is trained on. It contains all the words, all the subwords, all the characters that the model can recognize and process. The size and the coverage of the vocabulary directly impact the model's ability to understand and to generate diverse and accurate text. So here, a vocabulary is the set of unique tokens that a model is trained on. A simplified small example of this vocabulary is the following. As you can see, ChatGPT is an AI language model. So in this example, the vocabulary contains 6, from 0 to 5, so 6 unique tokens, words and punctuation. So each with an assigned numerical identifier. When a model processes text, it uses this vocabulary to convert tokens into numerical representations and the opposite. So keep in mind that real-world models use, of course, much larger vocabularies, often with tens of thousands of unique tokens. But here, as you can see, we have only 6 tokens, while in the previous slide, we had also full stop. So here, as you can understand, apart from the words, we should also have the final, the full stop. So this was the second. The first was tokenization. The second is vocabulary. The third is embeddings. Embeddings are used to convert tokens into continuous vectors that the model can process. So the goal is to convert all these tokens to vectors, continuous vectors, numbers that the model can process. These vectors represent the semantic and the syntactic information of the tokens and enable the model to identify the relationships between them. So embeddings are crucial, are really important for capturing the meaning of text and enabling the model to generate coherent and contextually relevant responses. So if we see again our example, let's create embeddings for the tokens in our vocabulary. Of course, in a real-world scenario, embeddings would have a very high dimension. For example, 300 dimensions or 768 dimensions. For simplicity, we use 2 dimensions, 2-dimensional embeddings, as you can see from the numbers here. So our vocabulary is ChatGPT, the first word, is the second, and the third, AI, the fourth, language, model, etc. So here are some example embeddings. The embeddings are continuous vectors that represent each token in our vocabulary. These vectors can be processed by the model to understand the meaning, to understand the relationships between the tokens. So in this example, the sentence ChatGPT is an AI language model would be represented by the corresponding embeddings of each token in the sentence. So what does these numbers mean? This is a very good question. The numbers in the embeddings are continuous values. So they represent each token in a multi-dimensional space. These values are generated by the model during the training process. They are generated by the model and they help the model understand the relationships and similarities between different tokens. Each dimension of the embedding space can capture a different aspect of the meaning or a linguistic feature. For example, one dimension might represent the level of formality, while another might represent the part of the speech. So the exact meaning of these dimensions is not easily interpretable by humans, as they are learned by the model during training. However, the position of a token's embedding in this multidimensional space, in our case 2-dimensional space, reflects the token's meaning and reflects the token's relationship to all the other tokens in the vocabulary. So tokens with similar meanings or tokens with similar usages will have closer positions in this space, where on the other hand, tokens with different meanings or tokens with different usages will be further apart. So these numbers themselves do not have a specific direct meaning. Instead, they act as coordinates in a multi-dimensional space, in our case 2-dimensional space, that the model uses to understand the model uses to process the language. These are the three very basic things. The first is tokenization, the second is the vocabulary, the third is the embeddings process. But here there are many more things that we should understand so that we can understand the transformer architecture. So the next one is the positional encoding. Positional encoding is a technique that is used to preserve the order of tokens in the input. It involves adding positional information to the token embeddings, allowing the model to understand and sequence relationships between tokens in the text. So positional encoding is essential, is vital for the model to generate contextually appropriate and coherent responses. As you can see, here is the sequence, I am a robot, index of tokens, 0, 1, 2, 3, tokenization, okay. So the next one is positional encoding matrix, having exactly where each token is positioned. Let's see an example together. In the positional encoding process, each position in the sequence gets assigned a unique vector. This vector is created using a combination of different functions with different frequencies. So for our example, we have two dimensions. Okay, let's use a simple example. The sentence is, I love ice cream. Without considering the position of the words, the transformer wouldn't be able to understand the difference between I love ice cream and ice cream loves me. So to overcome this, we use positional encoding. As we can see, one very easy way to do this is position 0, I, position 1, love, position 2, ice, position 3, cream. So these positional encodings would be added to the word embeddings of the corresponding tokens. This way, the transformer can now differentiate between words based on their positions in the sequence. In this way, it allows us to understand the context and to understand the relationships between words more effectively. So positional encoding is a very powerful technique used to position each token in a sequence, in a sentence, or a paragraph. So the next one is the self-attention mechanism. So here, self-attention mechanism is a key component of the transformer architecture because it enables the model to identify the relationships between tokens in the input. So by calculating specific attention scores between tokens, the model can focus more on relevant parts of the input when generating a response. This will lead to a more accurate and contextually appropriate output. So if I write an input, exactly as Google or other search engines work, it will calculate which tokens are more important by calculating the appropriate attention score between tokens. The next one is the scaled dot product attention. Scaled dot product attention is the core function of the self-attention mechanism that uses this transformer architecture. It calculates the similarity between tokens by taking the dot product of their embeddings and scales the result by a constant factor. This process allows the model to assign higher weights to more relevant tokens and lower weights to less relevant tokens. This assignment of the weights enables the model to focus on the most important parts of the input. The next one is multi-head attention. Multi-head attention is an extension of the self-attention mechanism. This multi-head attention actually processes input tokens in parallel. So we use multiple attention heads. Each head focuses on different aspects of the input, capturing a variety of relationships between tokens. So by combining the inputs of all attention heads, the model gains a more comprehensive understanding of the input. This will lead to improved performance and richer representations. The next one is layer normalization and residual connections. These are two techniques used within the transformer architecture to improve training, to improve stability, and to improve performance. So layer normalization scales and shifts the activations within each layer to have a consistent mean and a consistent variance that will prevent the model from experiencing issues like vanishing or exploding gradients. So residual connections, on the other hand, allow the model to learn more complex functions by adding the output of previous layers, of hidden layers, to the input of the current layer. This is the idea. And finally, we have feed-forward neural networks. Feed-forward neural networks are additional processing layers within the transformer architecture. They consist of fully connected layers that further process the output of the self-attention mechanism. These networks help the model learn more complex patterns, more complex relationships within the input, contributing to its ability to generate accurate, to generate contextually relevant responses. All this will lead to the output generation. Output generation is the final step in the transformer architecture. The model decodes its internal representation into human readable text. The model generates the output token and then the next token and then the next token, so token by token, selecting the most likely next token based on the probabilities it assigns to each token in each vocabulary. So it calculates the probabilities and then generates the output token by token by token. So all this process has a greedy, decoding, and beam search that are two techniques used for selecting the most likely token sequences during output generation. Greedy decoding selects the token with the highest probability at each step, while beam search maintains a fixed number of candidate sequences and explores multiple possibilities simultaneously. Beam search can often generate more diverse and more accurate outputs compared to grid decoding, but grid decoding from the computational side, it is more fast, more easy to implement, and it has less computational cost, exactly like all greedy algorithms work. And we have fine-tuning for conversational AI. So to adapt the GPT-4 model for chatbot applications, it undergoes a process called fine-tuning. This process involves training the model on a specific dataset of conversational examples, allowing it to learn the nuances, the patterns of the human dialogue. So fine-tuning helps the model generate more accurately, more contextually appropriate responses in a conversational setting. So it adapts the GPT-4 model for chatbot applications. Prompt engineering is the process of designing effective prompts that guide ChatGPT's responses. This is really important, and we will have next lectures specifically on this. So by carefully crafting the input prompts, users can change a lot the model's output, making it more focused, making it more relevant and informative. So prompt engineering is an essential skill for leveraging the full potential in ChatGPT in various applications. But controlling ChatGPT's behavior involves also adjusting parameters such as temperature and top K to influence the model's output. The temperature parameter controls the randomness of the output, with high values leading to more diverse responses, and lower values making the output more focused, more deterministic. Top K sampling limits the model's output to the K most likely tokens at each step. So this way, we provide a balance between diversity and coherence in the generated text. So controlling ChatGPT's behavior involves adjusting specific parameters for temperature and top K to influence the model's output. Temperature parameter controls the randomness, higher values leading to more diverse responses, lower values, more focused, more deterministic. Top K sampling limits the model's output to K specific tokens, providing a balance between diversity and coherence.